First of all, I would like to say I'm really happy about the new pointer, which I use the same one in my presentation now. I think these are super cool when they work.
I was just going to say, if they work, they're cool.
Yes, they work. And they don't always work very well PowerPoint either. But anyway, it's always a real pleasure to be invited back. You know, Michael's a glutton for punishment, I guess, so he's invited me back to yet another Knime Summit. Super fun. This community really is it's a different community than any other analytics community I've been a part of over the years. So I love being able to come and participate. And usually when I'm talking about things, it's what I happen to be thinking about in that period of time. So you're going to get a little bit of that with this presentation too. But because of things Michael said yesterday, I thought I'd start off with something I've never shown publicly, but I've been thinking about this as well. And it's kind of the promise of AI, the hype that's come around AI recently. So I thought I would introduce this with these quotes. So here are 5 quotes about AI. And think while you're reading the quotes, and I'll read some of them, when were they said? Okay, that's going to be the question you have. So the first one, you know, machines that think and learn and create all these great things that AI can do, the problems that they kind of solve. Someone else said, I'm optimistic about the eventual outcome of the work. Machine solution to intellectual problems. Within our lifetime, machines may surpass us in general intelligence. Okay? Machines will follow a path that mirrors evolution. Ultimately, however, self-aware, self-improving machines will evolve beyond human ability to control or even understand them. I mean, that's putting a lot on the shoulders of machines. I love all these. There's a whole bunch of these I could draw from. How far in the future before machines win and dominate? In 3 to 8 years, we'll have a machine that is the general intelligence of a human being. And the last one, it's likely that machines will be smarter us before the end of the century, not just at chess and trivia questions, but everything, mathematics, engineering, science, and medicine. So when were they stated? Like 2018, 2016, 2015. First one, 1957. And so, Michael, you're not that old, nor am I. But we're old enough to know that AI meant different things in the past, but the promise and the hype around AI has gone way back. The next one, Marvin Minsky, one of the huge AI proponents. I'm looking at John because have you ever met Dr. Minsky? You never met him. But 1961. Next one is from 2010, a futurist. So I really shouldn't bang on futurists too much because that's what they do. They try to come up with interesting, sometimes crazy things where society might go, like hovercraft, which is, you know, in every science fiction book and everything. It's hovercrafts coming in, even Back to the Future. That's where we're going to be. Of course, we're still driving with rubber tires on concrete roads. Marvin Minsky, again, Life magazine, 1970, 3 to 8 years. Those predictions kept on pushing forward another 8 to 10 years, like every 8 or 10 years, it gets pushed forward another 8 or 10 years. And the last one, Gary Marcus from 2013. So there you go, Michael. This has been around forever. You said it feels like deja vu, and I do feel like this is deja vu all over again. That stated, I'm not down on artificial intelligence by any means in terms of the analytics behind and the decisions being made from them. It's just, they are machines. And remember, this is something I said in my workshop 2 days ago, that algorithms, machines, they don't have common sense. They do exactly what they're told to do. So that's the hard thing to overcome, is how to get programs to quote unquote think. Okay, so the rest of this talk is not going to have anything to do with AI per se. I'm not going to say AI. I'm going to try not to say AI again, Michael, so that's all over. But I will say things about CRISP-DM. And I love the fact that this community is very tuned in to CRISP-DM. Not that CRISP-DM is the only way to describe this. You can describe these steps in lots of different ways. But as I tell everyone, I love CRISP-DM because it's documented in a PDF file that you can give to your boss and say, this is what I do, and it's actually understandable. And I just crossed out data mining because that's a 90s term, replaced with data science to be buzzword compliant and modern. I'm not going to say that other two-letter acronym, which we could apply the same process to. But I'm going to talk about a couple things for this talk in particular. The place most analytics projects fails, the place they fail is at the beginning, most often, by getting off on the wrong foot, trying to solve the wrong problem with the wrong metrics. And so I love in CRISP-DM, the first step talks about defining your business objective. What are you trying to accomplish with your analytics project? And the first part, the reason why I circled those two, is the top one, define business objectives. I strongly recommend teams, when I go in and speak with them, define it in the language of the business. Don't try to have analysts and analytics people try to shade or distort in a negative way or improve upon the business objectives. This is the way those domain experts, subject matter experts, the program managers are thinking about the analytics and how they're going to be used. However, we need to translate them because it's almost never the case that the business objectives are in the language that an analyst can either understand or do something about initially. You've got to translate that in some way. And then at the back end, it's success. I know this is really hard to do because sometimes we really don't know the answer to this question, but defining what success means for the organization is so critically important so we can translate the success criteria into the language of the algorithms. Now, the way I usually joke about this is probably about 15 years ago, I almost punted on machine learning because I was so frustrated that none of the projects I was working on had an objective that the organization was really interested in that I could solve and account for directly. I mean, what do the algorithms try to do? The algorithms are minimizing squared error. The metrics are using squared error, Gini, entropy, all these kinds of things. You know, if I start talking to my boss or who hired me about entropy and the information gain that I'm getting from this model, their eyes will glaze over, they're gonna throw me out of the room and say, show me something practical. They wanna know, how much money is this gonna make? How many hours is this gonna save? Those kind of business-centric things. So we have to translate them. But because machine learning algorithms don't minimize the right thing, we have to find a way to minimize what they can minimize and then translate that message into what the business is thinking about. So the reason why I almost punted, I said, we're minimizing, maximizing the wrong thing. Why don't I just use genetic algorithms or simulated annealing or something like that, which I can, and my initial skill set when I first had my first job was in variational calculus. So optimization algorithms. So how can we do this in a way that's flexible? The reason why we're all here doing, most of us are doing machine learning kinds of things, is because that is so hard to do. Those algorithms, they never converge, and you still don't get that cost function right because you've got to kind of invent what that is. So all these unintended consequences happen. You say, oh, well, it's not quite right. Let's increase the weight on this factor to see if the solution is better. Just like a lot of the clients that my company now, SmarterHQ, works with, they keep telling me, we want to be data-driven, Dean. Let the data speak. And they're fine with letting the data speak as long as the data tells the story they want to hear, right? And if it doesn't tell the story they want to hear, say, well, I want data to speak, but it's got to say these things. If it doesn't say these things, then I don't believe it. So this talk is going to be about those kind of ideas, framing the question and framing the metrics to judge how good models are. So let me give a very simple example that connects to John, actually, the early project in the 90s with the super exciting Defense Finance and Accounting Service, the government accountants. They're trying to determine what invoice fraud meant. And they couldn't use the word fraud, so they had to look for suspicious invoices. What they really want to do is when all these invoices, the million-plus invoices that arrive every month, come in, and before they pay them out, they want to screen them to see which ones could be problematic, have an auditor look at them in more detail, and then determine whether or not they're valid invoices or not. The requirement, though, is they could only examine, I think it was 100 invoices each month. That meant any predictive models we built would have to do well on that population. So let's put this in more practical terms. If you're getting 1 million invoices a month and you can only investigate 100 of them, what kind of model do you want to build? And I'm not talking about the algorithm, but what do you want the model to optimize for? And this is not a trick question. The answer is you want it to do as well as possible in that top 100 and minimize the false alarms or the true alerts in those top 100, and you literally don't care what happens in the rest of the file. It's irrelevant because you're never going to get there. And so that means algorithms that do well at global optimization are not going to be your best friend. The ones you want to rely on are the algorithms, or the way you want to bias the algorithms is to the tail, the very end of the distribution. So it completely changes the way you go about your modeling objectives to nail down what that objective is. So that's what this slide is talking about, the 100 invoices that we want to look at. So we don't care about all the invoices, only the top 100 scores. That metric makes a huge difference. Here's a couple examples, hopefully puts a little more flesh on this idea. This is a while back now, 2007, but all these scores were available online, and actually the solutions were all listed. And this is in the early days when model ensembles were starting to win competitions, and that's what this was actually trying to say. So all these are model ensemble solutions, by the way. But the winner was this particular solution, this stochastic gradient boosted machine kind of approach. And the metric they were using was the area under the curve, which has become a real popular metric people use for competitions. So here's the rank order. However, what if you used a slightly different metric? Because area under the curve, ROC curves in general, these are what I consider rank-ordered metrics because you sort scores from high to low, and then you compute the false alarm rate and the true alert rate as you change the threshold. So a ROC curve is essentially every confusion matrix possible in your data graphically depicted. And so it's a rank-ordered metric, but it's global. Area under the curve is the area under the entire ROC curve. Okay, from your perspective, it's like this. It's looking like this. You're just computing that area under the curve. What if you just looked at the top 10%? Which algorithms did the best job of picking out the top 10%? And this was a credit scoring kind of application. Here is the rank order there. Number 1 finished 3rd, but look at this. The number 2 top decile finisher was like number 20 in the list. I guess it is number 20. Different model would have been picked with a different metric, and not even a fundamentally different metric. This is just a little bit of a twist. Instead of looking at the entire data set, you just focus on that very beginning of the curve. I did this once with another data set, built thousands of models. And with those thousands of models, I had 2 different metrics. Area under the curve at the 70% depth versus the overall test root mean squared error. This is a regression problem. And this is just a rank correlation kind of plot. The correlation between the rank based upon AUC 70% depth and RMSE was 0. I just want to let that sink in for a minute. The way you compute what good means completely dominates or can completely dominate which model you pick. Now, this is not always the case. Sometimes every model you build tells the same story, so granted. But sometimes it matters a lot. Why? Algorithms have strengths and weaknesses. Some algorithms are very sensitive to the tails of the distribution, and they'll rank order well in the tails. Other algorithms are really good at kind of the middle of the pack. Logistic regression is linear, and it's really good at differentiating in the middle of the pack. It cares less and less the further away you get. So k-nearest neighbor can be very much dominated by outliers if your data is not sparsely populated. So each algorithm thinks differently about the data. So that's what I want us to think about. So here's the case study. SmartHQ, we get this question a lot. I want a customer lifetime value model. So first of all, for those of you who've been in the space, and I've talked with a few people here already, you first laugh right out of the box because almost nobody really wants customer lifetime value, right? They don't want to know what Dean's value is going to be in 2050 if I'm still alive then. What they really want is what is my future value over some time horizon so they can make a decision on what to do about me. That's in retail, because that's my company's larger in the retail world. So that's the first question. How valuable are your customers? And this is, you can Google search this and find dozens, hundreds, thousands of papers on computing customer lifetime value. And usually it's something along these lines: how much profit you can generate by retaining a customer based upon their future behavior. Now, a lot of times here, this is where my problem with the general methodology comes in. It's over the life of that person's time with you as a shopper. And I think most often, at least my experience has been most often with our clients, they would like to know that, but what they most want to know is, what is Dean going to do next week, next month, next 6 months, maybe the next year. So that's how customers view that. And here's a chart that a colleague of mine, Kyle Lee, put together. I think it's kind of helpful, looking at the different ways you could frame the CLV question depending on what your business is. There are some times when you're computing customer lifetime value when there's a contractual arrangement between the shopper and the business. Netflix, Amazon Prime, monthly renewals, annual renewals. So you're contractually obligated for that period of time, or credit card transactions. And then there's non-contractual ones where you just never know when somebody's going to show up on your retail site. They could show up next week, they could show up next month. There's no guarantee when they're going to come, and they're not required to come at a certain time in the future. And Kyle put that 5-pound gummy bear because he actually bought one of those as a birthday present for a friend, which, just the thought of a 5-pound gummy bear, I don't know what I would do with that. And so here's the way, statistically speaking, if you look at packages in R and Python, you get this kind of depiction. The classic customer lifetime value predictions are doing something like this. So this chart is showing in the x-axis, this is just transactions. Y-axis is an individual shopper. So a lot of these are one and dones. All these that don't have anything to the right, they purchase something here and they never purchase something again. Here's a shopper who had repeat purchases for a retail site. Another one with repeat purchases, fairly regular. Others have gaps in them. So you've got some people who purchase a lot, some people who purchase very little. What do you do about these people that are one and dones? Do you want to know what their likelihood of purchasing again are? I'm seeing both answers. It depends on the problem you're trying to solve, doesn't it? Because most of the packages we're using, that I'm not going to talk about here, I could talk offline about some of these packages for transactions. They're trying to uncover repeat purchases. So for everyone who has 2 or more purchases, this is what the model tells us. The one and dones they don't even care about because they don't have any information to identify repeat purchases. But let's do a thought experiment. If you're a retailer and you're thinking through what we want to do with this particular set of customers, we want to message them differently based upon what their anticipated value is going to be. Let's do a thought experiment. 2 shoppers. And you can see the things are the same about the 2 shoppers. One purchase every 2 months, average order value $150. Their lifetime value to date, historically speaking, is $1,500. Okay, so from a transactional perspective, they're identical, which means any model based upon transactional history is going to give the exact same prediction for both of them of what their future value is going to be. So here's the thought experiment. Shopper 1, no visits in the last 6 weeks. Shopper 2, 10 visits in the last week. Highly engaged in the site right now. So this is not rocket science, granted. But if you were to guess which shopper has a higher predicted, should have a higher predicted future value, which shopper would it be, right? So the whole point is there's additional information that's available to us that's outside of the parametric modeling approaches that you'd see for lifetime value, which is are just transaction-based, that we can and should use to incorporate into our models. So why do we use machine learning approaches for this? It's because you can have a flexible target variable, what we're trying to predict, and we can have flexible sets of inputs coming into them. We can customize this for any time window we're interested in looking at. So here are a couple Knime workflows. These are the prettier ones, like Paris was describing his got better. I have to say, for your workflows to look better as you use it more, you're a good man, because mine do not look better over time. They just look just as messy as they ever did. If I showed you the workflows I was working on for this, they're really messy. The nice thing about MetaNode is that you can just throw all that stuff. It's like sweeping under the carpet, right? You can just dump it all there. All the details are there. Nobody sees it. You can show this to your boss, and they can say, "Wow, you're so organized and so neat." I'm like, yes, I am. Just don't peek behind the curtain. Okay, so now I'm gonna, bear with me a little bit. I think it's important. I'm going to dive deeper than I usually dive in these, just to give you a peek under the hood of the things we think about with, remember, the big questions are, how do you frame the problem, and how do you judge what's good or not? Because what you do with the models is not necessarily going to be just look at model scores, okay? So here is an example with one of the clients. 87% of them were one and done with transactions. They purchased once and never transacted again in the past 24 months. This is typical, by the way, unfortunately, for most retailers. Now, one caveat. I'm saying they're one and done because we don't know necessarily who they are. They could come back to the site, delete their tracking cookie. We don't know who they are. They're anonymous from our standpoint. So you don't necessarily know. So this isn't necessarily a perfect depiction, but this is a good general depiction of typical shopper behavior. The other thing, look at so it drops abruptly. 87% are one and done. 12.8% had 2 or more transactions. If we drill down, and now we're removing the outlier, the one and dones, and looking at the 2 or mores, 47% of what's left are 2 or more, and we still have that really steep drop off. This is a hugely skewed, long tail kind of process. And that's what most retailers have to deal with. It would be so nice for some of these clients if it's like Starbucks and someone comes in every day or every week with regularity. It's really easy to predict what they're gonna do. It's really hard to predict what that person's gonna do if they've been twice or 3 times to the site. And you can keep on going through this. Every time you drill down deeper and deeper with your telescope, look at 3 or more, 4 or more, it's the same story. Super steep curve, like 40%, 40, 50% are whatever that number is, 3, 4, 5 transactions, and then the remaining 50% are more than that. So we know we're gonna have a long tail process, which tells us we're gonna have to do something with the data. Second thing, unit of analysis. What are we trying to predict? When you talk to your stakeholders about this business problem, one of the key questions is this: what decision is going to be made based upon this data? What decision is going to be made? If you're going to, and this was the case in our particular situation, we want, when a shopper comes to the site, we want to know how to message that shopper. We want our messaging to be at the individual shopper level. Now, if you're building a forecasting model to forecast total number of sales, acquisitions, churn, that's different. You could structure your data differently over some time bucket, which will be a smoother estimate and a lot cleaner, frankly. At the individual shopper level, it's going to be noisy, more granular, but more directly related to the decisions we want to make. And in this case, the target variable, when we spoke with some of our retail clients, they're mostly interested in having enough time to do something about it and give some people time to cure from any marketing messaging they're getting. So we were picking typically 30-day, sometimes 60-day. But we build these at the 1-day, 7-day, 30-day, 60-day level. And here's some of the data that's going in. Historic transaction data, of course. Historic average order value, historic lifetime value, and the bucketed versions of those. How many orders have they had in the last 30 days, the last 15 days? What's the total dollar value of their orders in the last 30 days, 15 days, et cetera. But we're adding other things like visit history and some other features that we create around shopper engagement. Why? Because when we're trying to uncover shopper intent, what do we think a shopper is going to do, how much we think a shopper is going to buy, everything they do in conjunction with the brand matters. Not just if they transacted, but what did they look at, how many things they look at, how many times have they visited, how many times they typically visit before they transact. All those kinds of features are valuable. So last thing, of course we know if we're building predictive models, we want to sample training and testing to make sure we don't overfit our models. And just as a precaution, when we sample, because we've got multiple examples of individual shoppers, because we're at the shopper day level, we're sampling randomly, throwing into training random customer IDs and all their transactional history and tests. We've got a separate set of customers. So we don't bleed over. We don't have the same customer in both training and testing data sets. Okay, what's the first thing we should do? Once we have the data set up, one of the first things I like to do is see what I expect is going to come out of the model. So I just did in this case, after all the normalization to get rid of the tails and all that kind of stuff, I looked at the correlation between the target variable and the inputs. And this will give me an idea of how good the model could potentially be. So that lead, I'm kind of a time series guy in the past. So I was thinking in terms of lag filters and lead filters. So I called historic data lagged versions of variables and my future, what I'm going to predict as a lead. So lead customer value less than equal to 30 days is the target variable. And we've got a bunch of the history. What's their customer value in the last 15 days, the last 30 days, the last 7 days? And how about that? The most correlated with what they will do in the next 30 days is what they did in the last 15 to 30 days. Now, frankly, if it didn't do that, I would be a little more concerned because that's the obvious stuff that we're expecting, just like predicting the weather. The best way to predict the weather tomorrow, unless you're in Austin on Thursday, is what the weather was like yesterday. But that's the typical thing. So you see, transactional history is the most important variable, one at a time, if you're going to pick any single variable. Then I ran through, thank you, Rosaria, for all of your great data preparation things. This is some of your typical things, low variance filters, correlations, all those kinds of things, just to prune down my data set from 92 down to about 74 input variables to this model. So then what happened? So first of all, what metrics are typically used for these kind of regression models? And this is kind of the typical thing people might do. R squared. Of course, I'm not going to tell my boss what the R squared is because he's not going to care. He's not going to know what it is, and he's not going to be able to interpret it. And I'm going to show you in a minute why even if they knew what it was, it wouldn't help them. Mean squared error, root mean squared error, mean absolute error, all these kinds of ways of judging what the aggregate value of the model is. But we're going to think differently about this. Instead of using R squared, we're going to use other metrics which tie into what the business is more interested in. So here's what the model showed, just looking at the same kind of correlation analysis. And the value of other data in addition to the transactions. So on the left side, this is the predicted value, and I'm seeing which variables are most correlated with our predicted scores. Obviously, it's most correlated with itself, but again, it's customer value, average order value have the highest correlation. Those are what's driving the predictions. If we add visit data, we can see that here's the overall correlation between the actual and the predicted, 0.54 correlation. And remember, these numbers, the fact that this is 0.872 doesn't say that customer value less than equal to 30 days is more predictive than the actual. It's saying what's more associated with the actual. This is driving the predictions, but the predictions themselves are just kind of middling. Correlation 0.54. When we add visit data, we're up to 0.62. Now we're going to look and see if that's important or not, but that's a significantly higher correlation coefficient, which means the visit data is doing something valuable for the models, that the original data, the way these problems are usually set up, occurs. Okay, so now how good is this in aggregate? This is a decile by decile analysis, looking at the data, and here are the prediction bins, the predicted scores, from $0 all the way up to, what's that, I'm trying to read that number, $21,000. It's got 3-digit precision, so we're going down to the fractions of a penny, which I should have gotten rid of those when I did my auto binner in Knime. But big numbers, 21,000. So here's what it looks like in aggregate. When you aggregate up to the decile level, it's linear. Relationship between the data and the predictions are linear. How does that help us, though? If we show this story, if you show that story to the boss, all you're telling them is, okay, we've got a reasonable correlation, we kind of get the idea of what's going on, but what are they going to do with it? And the answer is with R squared, with correlation coefficients, they don't know what to do with it. So let's think about what we can do with this. And let's break it up in a different way. And here I'm just breaking up those same 10 deciles, and I quintile the actuals. $0, people who didn't buy anything. $0 to $50, 50 to 100, meaningful buckets from the perspective of the retailer. Like what these kind of dollar buckets. And the top bucket is $20 or more. So let's look at a few of the stories the data is telling us. Number one, which is good, the lowest predicted bins, the ones that had the lowest scores, are almost always $0 shoppers. And this is on test data, by the way. There are a few which are outliers. One question is this: what happened with those 5 $200 shoppers that looked really bad? There's not that many of them. That's not the first place I'm going to look. But that's a question. What do we expect will happen if they've got the lowest predicted bin? We expect them not to spend a lot of money. Those that deviate from expected are the interesting ones. Those are the ones that could be potentially huge upsell. When you look at these, if you can characterize why these are showing up here, that can inform future campaigns to say, hey, they look really bad, but there's something else which we weren't measuring in the models that is driving what their future performance is. So that's the first thing to notice. The model is doing almost completely what it should do for those uninteresting cases. Now we've also got these at the bottom right. These are the ones that are in the top bins, and they're spending a lot of money. So I wrote here 2,300 of the almost 4,000 who transacted with more than $200 were identified in the top bin. So that's pretty good. That tells us, for the most part, the interesting thing is working just right. But what about these? These are people that looked really good but didn't do well. They did horrible. Look, at a whole bunch of them we predicted $0, and a bunch we predicted high dollar, but they actually only generated less than $50 of revenue. They're different. Again, the differences are what's the most interesting thing from a marketing perspective. What do you do with those? These are churn risk shoppers. Shoppers who you should be doing really well, and they're doing awful. Why? That's the question as marketers we're trying to understand, so that we can send them the right message, re-engage them, and get them back on the right track. Now, the other ways you could look at this exact same part, I mean, I just used the crosstab node in Knime and just check different boxes. Column percentages. So in this case, the column percentages are, these sum up to 100 down each of the columns. So 40% of those who actually spent $100, $200 fell into bins 9 and 10. And look at this, 78% of those who spent over $200 landed in our top 2 bins, which tells us our bins are doing the right job, doing the right thing. But there's also a big chunk here that $0 to $50 are falling in the upper bins. That's what we want to uncover. That's opportunity for upsell and more revenue. And again, this is row percentages instead of column percentages. So again, the story is when you fall into this bin, you're 40, 44, 45% of those actually spent a lot of money. So then how do we use the model? And this is just one suggestion of the many ways to use it. And this is something our customers have done a lot with our machine learning models, not using them the way that's super sexy, but just saying, hey, we're sending out an email with a discount. If they're falling into the high bin of customer lifetime value in the next, predicted value in the next 30 days, don't give them the discount. Let them do their thing. Let them make money. Don't lose margin on those that are going to do the right thing anyway, right? And that's just one story we can tell. Here's a second client. And I'm not going to go in nearly as much detail as the second client because we've got other things to talk about. Same kind of thing. 90% of them are one and dones. Same kind of correlation, a little bit higher for this case, 67%. The visit data improves it a little bit. And probably more interestingly, the ROC curve is significantly better. This is what the visit data does for us. It improves this area under the curve metric significantly just by adding visit data into the model, which in this case had to be a random forest model. Let me mention a couple last things. Speaking the language of the business. At the very beginning, I talked about this particular problem, customer lifetime value. What does speaking the language of the business mean? One of the things it means is starting from scratch with the business stakeholders and asking them what they want to achieve. We've had this, I was having this session with one of our clients recently. And they said, we want to know who is really engaged in the website. Can you tell me, can your company tell us how much time on site? How much time do they spend looking at the different products? How much time do they spend in a session on the website? My question was this: do you really want to know how much time they're there? What are you going to do if somebody spends 60 seconds versus 30 seconds on the page? What are you going to do if they spend 90 seconds instead of 30 seconds? What decision are you going to make about messaging them based upon the number of seconds that are on each of the pages? And they thought about it, and they didn't have a ready answer. And I said to them, I don't think that's the metric you really want. What you really want to know, what you're trying to use time as a surrogate for, is to identify how involved are they, how engaged, to use that term, are they on the website on that particular page. It's not just time, because we've all had experiences where you're on the website, you look at a page, hey Dean, can you come here for a minute? Walk over, page is still up, you come back, and 2 minutes have gone by and you've done nothing, because time just measures time. It doesn't measure involvement. So what they really wanted was a measure of how involved they were, and there are better ways to get at that answer. So sometimes that conversation with the stakeholders to get at the core question is not about the first thing that's coming to their mind or the way they've thought about the problem historically. It's having that conversation, cracking open that hood a little more to see what do they really want to know about this shopper. And one of the ways I get at that is with that question, what do you want to do if you knew something about that shopper? How is that going to change your strategy? Sometimes that's the clarifying question to help them understand what's going on, what kind of problem they want to set up, what kind of modeling objective they want. Use the models as an aid. From our perspective, as predictive modelers, we want the tail to wag the dog, right? We want the model to be front and center. The model gets plugged in, gets used directly, automatically, and makes tons of money for whoever we're building a model for. Many times, the primary purpose of the model is not to actually do something directly. It's to do something indirectly. We've seen some examples even today of models that are doing that kind of thing, where if the model gets placed into a system and it tells you what will happen if somebody changes their behavior. Because one of the things that my clients often want to know is, if we can take that shopper who's visited twice in the last week, if they visited 4 times instead of twice, how much revenue will that generate? Well, how do you do that? You build a model to predict their value with all these input features, find out the most sensitive inputs, and then you simulate. You change those to show you what the difference in the outcome is, and that arrives at that question. So in that case, the model doesn't actually get used directly. It gets used indirectly as a part of another process to tell you the answers to those what-if analyses. So the value of the model isn't always direct. And it's a good idea to think about interpreting the model. Why is the model behaving the way it's behaving? So that you have an idea of what things you can change about either behavior or processes within your organization to affect a better outcome. I did the same exact thing with a survey problem with the YMCA, where they wanted to know who is going to be most satisfied, who's likely to recommend to a friend. They wanted to change practices within the YMCA. One of the things we found is one of the most important things to change their sensitivities of how satisfied they were was, does the staff know your name? Right? And if the staff knew your name, if the people move from a 2 checkbox to a 1 checkbox, and the staff knowing your name, it was something like a 5% increase in satisfaction for the Y. Well, that's something you can take home, right? You can go tell your staff, have the greeter mentality, the Walmart greeter mentality. Go in, when they come in, say hi to them. When they're leaving, say goodbye and see you next time. And make the people feel more part of that community. So the model didn't tell you to do that directly. It told you to do that by uncovering what the model was doing and why it was doing what it was doing. I think I'm going to stop there. There's some other things I could do. There's other target variables that I was investigating with this. We could talk about that. Like, do you use a regression model? Do you use a binned version of it? What's the effect of stratified sampling in this kind of problem? There's a lot of questions to ask about this, but I think I'm going to stop and open up for questions.
Thank you, Dean. We have time for a few questions.
Hi, I kind of see a lot of what we do, kind of like the Fermi Paradox of where are all the aliens if they're out there. And, it's like if we have all these models, and they predict things that people find useful, where's all the money? Why is the, do you have these conversations with the business that, really, I don't know, in my mind, sometimes defy reality. It's like, I've shown you something that I think you can use, and you're still not biting.
It's always difficult from the retailer's perspective that views machine learning and that other 2-letter acronym that gets thrown into every conversation seemingly now, is that it's magic. That if we just throw data into a process, it'll automatically find all these customer profiles that we've never exploited before. Yes, we know that people who browse these different categories of women's shoes or other fashion, other apparel things, if they browse enough, they're more likely to convert in the near future. We want to know the underserved population. The problem is, of course, it's not magic. There's nothing magic. We define exactly the kind of thing we want. And when I have those conversations with them, one of my questions is, what kind of population are you looking for? Because the population they're looking for, they still say underserved. Okay, so let's try to understand what an underserved population means analytically, because I've got to eventually write the query, right, to pull out the data which represents underserved. And it's because it's viewed as magic, you have to unravel that to get to more specific situations of what they're really interested in. What they really want to know is, are there patterns of behavior of shoppers that we're not targeting with our messaging that we could target with messaging that improves the outcome, generates more money for them? And that's, you've got to define it up front. The other way I say that to them is, any audience we generate could be a good audience if you said the right message to them, right? Because you could have an audience that is the rock star audience. They're always buying stuff. There could be some margin for improvement. some upsell opportunities with them. So even the best audience could get better, and even a bad audience, a small increase, because most shoppers are really bad, right? So a very small, marginal 10%, even 1% lift in a bad audience can generate good revenue numbers for you. So it's hard. It's hard to get them to sit down long enough to think about what problem they're really trying to crack. So you're right. There's a lot of the unknown unknowns, but you have to define it, and you've got to define it precisely before you build models to try to solve for that particular problem. And the error metric is critical. Do you just want more visits to the site? Do you want more revenue? What is the purpose of the model? What are you trying to accomplish directly?
Hi, Dean. It's always awesome to hear you talk. And I just want to add on to that question. And you start with the crisp DM process. A lot of times, a majority of the time, in fact, what I see is it's never a circle. It's always a spiral. How do you have a process to get the business to re-engage with the model at the original problem, to revisit it and kind of optimize that original question and revisit the modeling process?
Yeah, I think feedback is a critical part of the process, and you're absolutely right. I don't view Chris theme is kind of circular. It's helpful that it has some of those feedback loops, but those are only a few feedback loops. I mean, so having your business stakeholder engaged throughout the process is critically important. Data preparation. You're building features. What features should we build? I mean, I don't know. I mean, I think you were mentioning that the data preparation part is the one part you said that's very difficult, if not impossible, to automate. And that's why the other joke I tell is how many data preparation books have you seen out there for data science, data mining, et cetera? There's one that's published that's of any significant circulation out there. Though I do know somebody who's writing another one right now, which I can't wait till it's finished. But it's incredibly hard because there's so many ways data can go wrong and so many ways that data is just different. The kind of features you build depend on the application. So engaging them at that stage to say, these are the things I'm thinking about. When you think about this problem, what other things come to your mind so you can try to bring that data to bear and create those features, ratios, interaction effects, all those kinds of things that are hard for machine learning algorithms to find. The modeling, fast feedback after you build your first model to show what it's doing, tying it into what that objective that you tried to nail down at the beginning are, so they can get early feedback to see, is this doing what we expect to do? One of the big places I see model processes fail, at least personally and anecdotal stories, is when the data is thrown over the wall to the analytics team and they've got 6 months to come up with something, and then they finally come back with the answer. And it's like an open loop process where the further you go, the more it diverges from what the expectations are. There's always going to be terminology problems with the business stakeholders if they're not data scientists and the analysts. So I usually recommend, especially when companies are starting out with the process, do smaller, tactical, quicker hitter kinds of projects to get the stakeholders comfortable with the language and the process that's involved and get the analysts familiar with what the expectations are. And then you can see the benefit quickly and before you take on they try to hit the home run. James Taylor, who is a business process guy, has a great slide that sometimes I show, and I didn't show it today. He tries to get at the value of strategic decisions and tactical decisions. And there are thousands of tactical decisions a company needs to make, and there are a few strategic decisions. So what we want to do is really go straight for the strategic, because that's going to have the biggest monetary impact. However, he argues that many times, in aggregate, the 10, 50, 100 tactical decisions will have more benefit to the company than the one strategic decision change. And those are a lot easier to build. So that's why I'd say try to start smaller, lots of feedback. And if your boss who's driving the process does not trust analytics, you're in a lot of trouble. You've got to find ways to at least crack that door open and tell a good story. And the best way is with success, showing some good value from the models. Even if it's not predicting the right thing, if it's uncovering things about the process that they didn't know before. That's, to me, the ideal story. You build a model, and 80% of it, they say, or 90% of the model, they say, I don't need machine learning to tell me that. No, it's obvious. But there's a few things that are like, no, I didn't know that. That's pretty cool. Now, the one dirty secret of that, they'll say that I knew like all these things that you're showing the model. They really didn't. They suspected it, but they didn't know exactly what the threshold or cutoff would be. They didn't know the relative sensitivity. They didn't know how it fit into a broader context. They don't know any of that. They just know, I mean, when our models say, yeah, customer value less than equal to 30 days is the biggest driver of what people do in the next 30 days, I was like, yeah, duh, of course. But how important is it? If you change it from $100 less 30 days, if someone has $200 less 30 days, how much does that actually matter? Will that change your marketing strategy if you knew that difference? They don't know the answer to that question.
Cheers, Dean.
Thank you, Dean.